I'm gonna start. Okay, okay. Today I'm gonna talking about accelerating deep learning computation. Yeah, I'm a Professor Marcelo Fernandes from Federal University of Rio Grande do Norte in Natal, Brazil. Okay, and I'm gonna I start tutorial T5. Okay. Let's go. Oh, sorry. Okay. This is our agenda today. Okay. I'm gonna talk a little bit about motivation, about deep neural network. Yeah. Of course, I'm not explaining about the deep neural network, but for me now, deep neural network it's a computer with several unit processes. Okay, it's an important point to this tutorial. Yeah. And after, I'm going to talk about the taxonomy of acceleration strategies, okay? And I'm going to talk about algorithm-based acceleration and model optimization and learning and system-based acceleration, okay? Let me talk a little bit about my lab, okay? I'm in Brazil, in the city is called Natal. Natal means Christmas, okay? This is the lab that I'm working, okay? And I'm a leader of a research group and embedded system in reconfigurable computing. And I'm also leader of laboratory of machine learning in intelligent instrumentation, okay? This is that lab that I'm a leader. That's some students in our team. Yeah, and in our lab we have been working with digital signal processing, artificial intelligence, and hardware. Okay, and we are using all these areas. Okay, all these fields in several applications like telecommunication, tactile internet, bioinformatics, robotics, and so on. Okay. Okay. So let me talking about the motivation. Yeah, it's interesting. You understand, guys, that there is two big motivations that we need to accelerate deep learning algorithms. Okay, the first one, it's about the massive data. It's about the growing demand for data process. Yeah, yeah. Today we have many data. Yeah, we have many massive data sets, big data, and a lot of things. Yeah. We have been generating data, yeah, many data, yeah, and on the other hand, nowadays we have a big demand for artificial intelligence algorithms, yeah, in specific in machine learning, in deep learning algorithms, yeah. Today it's a common thing, yeah. I worked with artificial intelligence since 2000, okay, 21 years, yeah, and I saw this concept, yeah, artificial intelligence, yeah, 20 years ago, just professors, just scientists talking about, yeah. Today, every people talking about machine learning, talk about deep learning, yeah. It's it's this concept. Yeah, this is in the family dinner, in the family barbecue. Yeah, but it's interesting because you have a growing demand of data processing, and we have a growing demand of machine learning or deep learning. Yeah, but deep learning, yeah, needs a high computation, and this is a point now, yeah, because we have two big problems, because deep learning needs a high computation, and we have many data to process, yeah. So it's a very big problem, and we need accelerate deep learning algorithms and deep learning approach. Okay. This picture shows that how the processing in deep learning growing up. Yeah, and you can see that today we need several petaflops a day to process. Okay, and this paper, it's so interesting, because this paper shows that how these machine learning approach, these machine learning algorithms demands of power consumption. Yeah, some some data centers like Amazon, Google, Microsoft has consumption equivalent to some countries, yeah, some renewable energy countries. Okay, and this is a interesting point and a problem too, yeah, because we have today we have high process, but we need high power consumption if we will use high process. Yeah, and this is a problem. Yeah, because we need we will need high processing with low power. Yeah, so it's necessary perform machine learning and deep learning with high speed or high throughput. Yeah, it's our target. We need processing machine learning and deep learning with high throughput. However, we need power efficiency. Yeah, and the other words, we need high throughput but low power. It's important, yeah, because that I said, today we have high throughput, but high throughut it's equal a high power consumption. This is not good today, yeah. And sometimes we need a low size hardware too, yeah. If you imagine in IoT problem, for example, imagine, for example, you put a hardware in the shirt button, for example, and I imagine that inside the button we will have a machine learning or deep learning algorithm. How I embedded, how I put a deep learning algorithm inside in the low size hardware, because IoT system will need a low size hardware. Yeah, this is an important motivation. Yeah, this topic is important talks about this tutorial. Yeah, we need high throughput, but high throughput with power efficiency and low size hardware and other filters, okay, and the other filters, okay. So this is a big figure that I said, yeah. We have massive data and data growing, always growing, yeah. We have a high demand to machine learning and deep learning applications, and these guys needs a high computation and growing up too, okay. But we need performance with high throughput, low power, low size hardware, okay, and the other, okay. So why deep learning acceleration? Yeah, we can accelerate in training, yeah, because networks can be very large and the training is time consuming and expensive, yeah. This is a problem, yeah. You know that about, because we several times wait to training, yeah. I think that many machine learning research spend many times waiting to training, yeah, to machine learning training, yeah. And of course, we need accelerating inference process, yeah, because a real-time application, low energy, in real-time application, we need a low energy inference with a small model footprint on the smartphone edge and in the other, yeah. Okay, it's important because in this tutorial, I'm gonna talking about the accelerated training, yeah, but the main focus is in accelerating inference, okay, because accelerated training it's a little bit complicated yet, okay. Today we have advanced in accelerating inference. And I think that we need more time to create new strategies to accelerate training, because it's a big challenge, okay? But of course, we can do that, okay? And of course, we can accelerating processing in the edge instead of the cloud, yeah, using federated learning, distributed learning, and others. Okay. This picture, it's also about motivation. It's about the red line here. It's a more low, yeah. It's a theoretical, yeah, more low. And this other line here, it's a practical, yeah. It's a practical situation, yeah. It's a real situation of the processors, okay. So now, today, we have a big problem because the traditional, okay, traditional computer or traditional architecture of computation, it's in the limit, yeah, and that I said before, we can high throughput, but there is a power cost that when you increase your throughput, this is a problem. Yeah, this is a problem. If you can low power, you need to get another way. Yeah, another way, another path. Okay. So a little bit review about convolutional neural network. Yeah, everything that I'm gonna say here. Okay, I'm gonna talk here. You can use to several deep learning architectures. Okay, but in this tutorial, because I have a limited time, yeah, I'm just we will use convolutional neural network, okay? Okay, but of course, everything that I'm gonna talking here, you can use for other architectures. Okay, so just a little review. Yeah, we have filter extraction. Yeah, the several layers with filter extraction. Yeah, that we making a convolutional processing, and we have a fully connected part. Yeah, that we make classification, prediction. Yeah, okay. So if you look more in this deep learning or deep neural network, we can see two kinds of neural. Yeah, the if we get the fully connected, yeah, we have this type of neuron, yeah. It's a product neuron, okay. I call it 1D dot product neuron, yeah. It's a dot product, yeah, that we have the weights, yeah, and that we have the inputs, yeah. This is a processor unit in the fully connected part inside of the convolutional neural network, yeah. It's important you see, because for us now it's important we see the parts of the convolutional neural network with a processor unit, okay. So in the convolutional part, yeah, we have a little bit more complicated processor unit, yeah, a little bit more, okay, because you know that we have several kernels, yeah, several kernels. Of course, we can we can have two-dimensional kernel or one-dimensional kernel. Yeah. In this case, in this example, I'm using a two-dimensional kernel. Yeah, it's more common. Yeah, to in a convolutional neural network. Yeah, and we have here just a kernel. We have here input. Yeah, and here we make a convolutional processing, yeah, and each kernel generate another bidimensional output. Yeah, we have a bidimensional input, we have a bidimensional kernel, and we have a bidimensional output. Yeah, and we have these operations for each point in this two-dimensional structure, yeah. And I call it here, it's a 2D dot product neuron, yeah, because it's a dot product too, okay, but it's a bidimensional, yeah, because this operation it's like this operation too, yeah, okay, but it's a two-dimensional, yeah. Of course, it's we need make several methods like that, yeah, and we have a two-dimensional convolutional neuron, okay. Each kernel in convolutional part inside the convolutional neural network, yeah, it's a convolutional neuron, yeah, and inside of the convolutional neuron we have several DPN dot product neuron. Okay, I call it with this name just we make more easy to understand. Okay, so we have two types of neuron. Yeah, we have a 1D DPN. Yeah, in the fully connected, and in the convolutional part we have a 2D DPN, or we have a 2D CN. Yeah, because a convolutional neuron it's a group of the 2D DPN. Yeah, okay, so it's we have many processors units. Okay, so this is a very big figure that we can see every processor unit, okay, inside of this convolutional neural network. Okay, we have many layers in the convolutional part. Yeah, and we have many layers in the fully connected part. Yeah, of course, in the convolutional part, we have other kind of the processors like activation function, pooling, okay? But for us now, activation function in pooling is not so important, yeah? Because of course, you spend some time to processing this function, to processing this other function, but the more complex part of the convolutional part, yeah, is the convolutional operation. Yeah, so for the moment, okay, I'm gonna forget these processors, the activation function, pooling, okay, because for me now it's a easy part to do. Okay, of course, you spend time to do that, but for now it's not important for us. Okay, because these guys are more expressive. Yeah, spend more time to process. Okay, to process, and these guys too. Okay, yeah, and of course you have many processors units. Yeah, and this is a problem now. Yeah, because I need perform everything with high processing and low power and the other features. Okay, so the question is, how can I speed up the inference process? How can I speed up? Yeah, there are many ways. Yeah, for example, okay, I'm just put some free ideas here. Okay, yeah. For example, each layer with a CPU core. It's idea. Yeah, I think it's a way. Yeah, I put each layer with some CPU core, and I can accelerate. Yeah, it's a way to accelerate. Yeah, it's important because every approach that I'm gonna show you, it's associated with architecture of the machine learning or deep learning. Yeah, or it's associated with the algorithm. Yeah, the training algorithm. Yeah, the values of the weights. Okay, but for example, I can put each layer with a GPU core. Yeah, I can accelerate this processing using GPU, yeah, it's simple because inside the GPU, I have many cores, thousands of cores, and I can put each layer, yeah, or each processor here inside of the core, yeah, yeah, or each layer with a machine. For example, I can make distributed computing. For example, yeah, I can put this part in the machine. I can put this part in the other machine. For example, yeah, I can make a distributed processing. Yeah, or I can develop a specific hardware. Yeah, it's possible. It's possible. I'm gonna create a specific hardware, a specialized hardware, a ASIC to execute to perform all these elements. Yeah. The problem now it's about the specific hardware. It's about the size of the deep learning. Yeah, because now we will insert many layers, many neurons, many processor units. Yeah, and this is a big problem. Yeah, but this is a way. It's it's important you understand that there are many ways to accelerate deep learning. Yeah, it's not specific or complexity way to accelerate. You can make many. You have many simple alternatives to accelerate deep learning. Okay, but now there is some ways. Okay, some paths that research have been used to accelerate deep learning. Yeah, I did a big division, but it's important you understand that some authors make other divisions. Okay, but I tried simplify in two big divisions. Okay, in two big families of the acceleration strategies. Okay, but that I said, there are other subdivisions. Okay, it's important you understand. Yeah. Okay. In my taxonomy here, yeah, I divided in algorithm-based acceleration strategies, okay, and system-based acceleration strategy, okay. I did these big divisions, okay. So the idea of the algorithm-based acceleration is you are preoccupied with just the algorithm, okay? How I can optimize make optimization in the algorithm, yeah? Of course, because if I make an optimization in the algorithm, yeah, I can accelerate, okay? I can accelerate. I don't need change the hardware to accelerate a deep learning inference, for example. Yeah, I can use the same hardware, but I can accelerate changing the algorithm. Yeah. Okay. So when I say about algorithm, I did three divisions. Okay, sparsity exploitation, model compression, and model optimization learning. Okay, that I'm gonna talk after. Okay, and when another big division, it's a system-based acceleration, and we can divide it parallel processing, okay, data and model parallelism, memory system for minimizing data movement, yeah, hardware accelerators, okay. So in this case, I'm gonna create a specific hardware, okay, a dedicated hardware, a specialized hardware, and distributed computer, yeah. And you can see that the second part, yeah, is more about the structure, yeah. I'm gonna change the deep learning structure. And the first part, I'm gonna change the deep learning algorithm to accelerate the process. Okay. Of course, I can use both. Yeah, I can use many strategies together. Yeah, it's not separate strategy. Yeah, I can use many strategies together. Of course, each strategy that I'm gonna use it, I have a price. Yeah, uh, I'm gonna have a price. Yeah, of course. That if I'm making a compression, yeah, if I will use a model compression, I can increase the speed up, but I can lose the accuracy. Okay, I can decrease the accuracy. Yeah, everything that I will show you now, there is a price. Yeah, of course, of course. Okay. We're gonna talk now about sparsity exploitation. Yeah, the idea here is you don't see the structure because it's a algorithm based acceleration. Yeah, so you don't preoccupate with the you don't worry with the structure. Yeah, this I don't concern about the structure. Yeah, and I just see the algorithm or the weights. Okay, the weights of the deep learn. Yeah, the deep learn parameters. Yeah, okay. In many cases, okay, in many applications, if you see weights in the neuron or in the layer, you will see these distribution. Yeah, this graph here shows the distributions of the weights in the specific layer. Okay, okay. This is a histogram of the weights. Okay, so you can see that we have the many weights are close to zero. Yeah, in this case, for example, many weights are many weights values. Sorry, many weights values are close to zero. Yeah, so if I have many weights close to zero, I can remove these weights, because if these weight values are very little, I can remove it. Okay, this is a sparsity exploitation, because we have a sparsity in the weights. Okay, if we see the weight in the all CNN or in the specific layer, you see a sparsity. Okay, you have many zero values. If you have many zero values or many values close to zero, you can remove it. Okay, yeah. So you can see the sparsity in a bit level, in the value, in the channel, in the filter. When I said filter here, it's a kernel in the block. Okay, you can divide your CNN in several kinds of sparsity filters. Okay, in this example, okay, we have more than 5,000 values less than 0.01 and about 2,700 values less than 0.0011, okay, and 1,700 values less 0.001. Yeah, I can remove it, these values. Yeah, because these values are very, very close, or very, very close to zero. Yeah. So if we remove this, if we remove some weights, we can accelerate. Yeah, can accelerate process. We don't need change the structure. We don't need change the hardware, but we can accelerate because we don't need make all weights. Some weights are zero. Yeah, are zero. So I don't need calculate this weight, and I can accelerate. It's yeah, and there are many strategies that you can do. Okay. Sorry. And another way that we can make it's a model compression. Okay. And when I said model compression, we have three ways here. Yeah, we can make a quantization. Yeah, we can reduce the bit width. Okay, the size of the bit. Okay, we can make a pruning. Yeah, it's an other strategy. Yeah. Or we can use a fine-tuning pre-training. Yeah, pre-training. Pre-training. It's a very easy way to accelerating a train, for example. Yeah, it's you don't need start your training from zero. You can use a pre-training model. If you use a pre-training model, you are accelerating your deep learning. Yeah, it's a very simple scheme. Yeah. Now let me talking about the quantization. Yeah, I'm gonna talking about model compression, weight quantization. Yeah, the idea is make a quantization. Yeah, in the weights. Yeah, it's interesting because there are other approach that some people make a quantization in the activation function. Okay, but in this case, I'm just show you how we can make weight quantization. Yeah, there are many strategies to weight quantization. Yeah, in this case, I'm showing I'm showing the linear quantization. Okay, but you can use several strategies to quantization. Yeah, in this picture, for example, we have a float point 32 number, and we can quantize to 8-bit integer number. Yeah, it's interesting because you can save 4 times in the memory access, yeah, and you can save many power if you don't use 32 float point and integer 8 bits. Okay. When I talking about weight quantization, okay, we can make quantization post training or aware or during the training. Okay, there are 2 ways. I can make quantization after the training. I training my deep learning, and I can apply a quantization strategy. Okay, it's working. Yeah, it's working, and it's a very simple scheme that we can save power. Yeah, of course. If you quantize, if you make a high quantization, you decrease your accuracy. Yeah, but there is there is a level that you can make a quantization and you don't decrease accuracy or decrease a little bit your accuracy. Okay, and there are another strategy that called the quantization-aware training, that you making the quantization during the training. Yeah, it's more efficient, this strategy, than this one. Okay. In this case, I'm show 2 ways that you can make aware quantization. Okay, quantization during the training. Yeah, it's a little bit. It's a it's a simple way. Okay, in the left side, it's a first scan. Okay, there it's like you have two DNN works in parallel. Okay, you have the training part, and you have the inference part. Okay, and the training part you making in a float point, for example. Okay, you execute this part using the float point. Yeah, and each iteration, or in the n iterations. Okay, you can wait for 10 by 10 iteration, or iteration by iteration. Yeah, when I say iteration, I'm saying about the mini batch. Yeah, you can make each mini batch, or you can wait several mini batches and apply the quantization, and wait more several mini batches and apply again the quantization. Yeah, so you execute this part in the float point, and the another part you perform in the quantization. Okay, you make the quantization. For example, if you use 8-bit here, you will work with 8 bits. Okay, 8 bits. Yeah, but calculate your gradient, and your gradient goes to the weight update. Yeah, you get it. Your weight update is in float point, but the inference part, the gradient calculation, is with 8 bits. Yeah, 8 bits. It's a way to to making a aware quantization, yeah, or quantization-aware training. Yeah. Another scam is this one that I'm showing you in the right side. Yeah, that you got the gradient before the quantization. Yeah, in this part I got the gradient after quantization. Yeah. It's a little bit different, but you can have different performance. Okay. I'm going to show you a case study. Okay, a specific case study. It's a very specific case study. It's about the virus classification, because I have been working with virus classification. Okay, so this is just an example that we have 4 viruses, and the CNN, yeah, needs to classify that virus. Okay, and I'm gonna show you that the performance that you use quantization. Okay, this is a deep learning that I use it. Okay, to get these results. Okay, and in this case it's weights. Okay, this is a histogram of weights. Okay, this is a 4 layer. Yeah, it's a convolution, is the first convolution layer, the second convolution layer, the fourth, and the third. Okay, it's the all weights. It's the weights distribution. Okay, and this is a confusion matrix using 32 bits. Okay, in this case it's a normal case that I'm not use quantization. Okay, in this case I use it 8 bits quantization. Okay, and you can see that my accuracy is very similar. Yeah, but now I'm using an integer 8 bits. Yeah, it's not float point. Okay, in this case I'm using this scam. I think I don't remember now. I'm sorry, but it's very similar. Okay, so in the another case, this is a aggressive quantization. Yeah, I use it 4 bits. Okay, 4 bits. Yeah, and you can see that the accuracy it's similar. It's very similar, but just using 4 bits. Okay, and in this case I use it 3 bits, just 3 bits. Okay, for each weight. Okay, and of course my accuracy decreased. Yeah, of course, but my accuracy it's good. Yeah, it's good, above 19%. Okay, for each class. Yeah, so it's very interesting, because we had 32 bits, and now we have just 3 bits for weight. Okay, it's a very aggressive quantization. Yeah? Okay, and another way, it's it's weight pruning. Yeah, it's another kind of model compression that we can use weight pruning. Pruning is a simple strategy that we can remove some connections or some neurons. Yeah, you can make pruning in each neuron or by connection. Yeah, and there are many strategies that you can use to decide if you remove or not remove some connection. Yeah. In this case, yeah, I'm using a strategy that I calculated pruning cutoff. Yeah. Pruning cutoff, it's a parameter that I call it beta, okay? And Pruning cutoff, it's equal alpha times standard deviation of the distribution, okay? Okay. So the idea is it's remove all connections close to zero. Yeah, all remove. You remove all connections close to zero, but you can use several decision algorithms. Yeah, to choose how weight you remove. Yeah. This is a strategy that pruning, yeah, aware pruning, yeah. The pruning is the during the training, yeah, and you can make pruning each mini batch, or you can wait several mini batch and apply pruning, and after wait more several mini batch and apply pruning again, okay, or you can apply pruning each mini batch, okay, each mini batch. The idea is it's similar to the quantization, yeah. This part you don't have pruning, and you just pruning the inference part, okay. But you get the gradient calculation from the pruned values, and you apply the weight quantization, okay. And this is some results for the same example that I present, yeah, the virus classification. Yeah, in this case, I did this pruning, okay. It's a very aggressive prune, yeah, but you can see that the accuracy decreased, but not decreased much, okay. And in this case, I was more aggressive. Yeah, I pruned several values. Yeah, several values. Yeah, of course, the accuracy decreased. Yeah, but depends of the application. Yeah, of course. Yeah, but not so much. Yeah. This is another strategy, okay, that is a little bit different, yeah, that you make a pruning, because in this strategy, you make a copy of the weights. Here, no, yeah, the pruning weights participate of the weight update, okay. In this case, we have a little bit, we have a different profile, yeah, because you can see that several weights I stay very close with zero, and when you make the pruning, yeah. And you can remove these guys here, okay. It's interesting because I don't know if you realize, but this strategy create two distributions, okay. Yeah, before we have one distribution, yeah, one Gaussian distribution, and now we have two Gaussian distribution, yeah, out the Pruning cutoff, okay. This is okay, sorry. This is other way that we can make together pruning and quantization, yeah. In this strategy, I'm using pruning followed by quantization, yeah. I can be more aggressive now because I can make pruning and quantization. Yeah, this is weights, okay? Yeah, and this is a confusion matrix, yeah. This is other strategy, yeah. That strategy and the other one, but pruning in quantization, yeah. That we can make pruning followed by quantization, yeah. Again, you can make this one each mini batch, or you can wait several mini batches and apply running quantization, wait more and apply again. Okay, and this one it's a new one. Okay, this strategy that I'm published in this conference, okay? It's a new one that we use quantization followed by Prune, okay? It's we change, yeah. It's we can have more aggressive quantization in Prune, yeah. And the accuracy, this strategy, it's better than Prune followed by quantization, okay? And we have two approaches. This approach and our other approach. It's a little bit different, yeah. That we can change the blocks, okay, inside of the train, okay, inside of the train. And some comparisons with quantization and quantization followed by pruning, and pruning followed by quantization. Okay. Okay. This model compression, yeah, that I said about pruning and quantization, and another one is model optimization and learn. Yeah. This strategy, it's also algorithm strategy, yeah, because it's algorithm based acceleration, yeah. But in this case, we transform we can transform the model, yeah. For example, we can use FFT, yeah, to in the signal, yeah, and make the convolution in the frequency domain, yeah. Or you can separate the kernels and they optimize the structure of the kernels operation, yeah. Or we can use student-teacher distillation, yeah, to train, optimize it, or reduce it deep learning. Okay. In this strategy here, the authors using the FFT to make a convolutional, yeah, to make the convolutional operation. Okay, so you know that in the time domain, the convolutional operation, it's complexity, yeah, because you have two windows and you can make the all operations, yeah. But when you transform the signal to frequency domain, in frequency domain, the convolutional, it's just a multiplication, okay? And you can reduce the number of operations if you transform the information to frequency domain. Of course, you spend time to make this transformation, yeah. But in some cases, it's you have more advantage if you transform your information to frequency domain. Okay. And another case here, it's a student teacher distillation. Okay. That we have a pre-training deep learning, and this can train another deep learning, but you train a reduced deep learning. You have the the teacher, it's a big one, deep learning, and teacher training student, it's a small one, deep learning. Yeah, and you can create more fast deep learning because you have a small one. Okay, a small one. Yeah. Okay, and now I'm gonna talking about the system-based and acceleration. Yeah, we have now we already have 1 hour of the tutorial. I don't know if someone would like to make some question now, because I think now it's a half in the half time of the tutorial. I don't know if someone would like to make some question about that I said until now. No? Okay, don't go ahead, okay? Now, I'm gonna talking about the system-based acceleration, okay? So we have a parallel processing, yeah, and data and model parallelism, memory system minimizing data movement, hardware, and distributed computing. Okay? Sorry. Yeah, the parallel processing, yeah, in data and model parallelism, it's interesting because it's associated with the hardware. Yeah, if you have some specific hardware, you can make some parallelization. Yeah. And of course, you can make execution of the several samples in parallel, or you can use GPU, for example, to make a data parallelism. Okay, or if you making a model parallelism, you can use a specific hardware. Yeah, for example, a systolic array based processor, yeah, TPU, okay. It's interesting because it's not it's like a hardware accelerator, okay, but it's a little bit different because when I'm gonna talking about the hardware accelerator, I will have ever freedom to create a hardware, yeah. In this case, no. Yeah, in this case, you have commercial hardware to make a process. Okay. So it's can I show you again the structure? Okay. Now, before we talked about the algorithm. Okay. Now we will talk about the structure, yeah, because when we use data parallelism or model parallelism, yeah, you can make some part of, okay, some unity processor, okay, in a specific core or in a specific part of the hardware that you have, okay. In several cases, you can use systolic array. Okay, systolic array. It's a very interesting way that you can create a specific hardware, or some companies can create a specific hardware to processing metrics operation. Okay. systolic array was created with Professor Prune in 80s, okay? But now several works and several research and several companies have used systolic array or systolic architecture to making accelerating strategy to deep learning. Okay, systolic array, it's a way to make a matrix operation. Okay, with a high performance. Okay, it's a good way to make a matrix operation. Okay. And for example, if you see a Google tensor process unit, yeah, TPU use a kind of the systolic array, okay, to accelerate their deep learning algorithms, okay. So another way to make accelerating a strategy, it's it's a memory system, yeah, because you can see from this picture that many power consumption, it's associated with the data movement between processor and memory. Okay, if you reduce this movement, you can reduce the power consumption. Okay. So this is idea of the data movement optimization, yeah. And we have the NVM memories, okay, and that 3D memories, okay, that you can associate the memory and the in the processors in the same structure, and you can reduce the data movement between processor and in memory, yeah. And of course, you can use a high bandwidth SRAM, yeah, local SRAM, to reduce these data movement, yeah. And you can accelerate, okay. And the next one, it's about the hardware accelerators, okay. The hardware accelerators, the idea is you create your hardware. Yeah, you create a specific hardware, specialized hardware to make deep learning unity processors. Yeah, again, the idea now is why I don't create my hardware to do this one. Yeah, that idea this is idea of the hardware accelerator. Okay, it's create a specific hardware to each unity processor or several unity processors. Okay, of course, today we don't have deep learning processors where each unit is a specific hardware unit. Okay, but if you can do that, you can accelerate, and you can have a high accelerate. Okay, your deep learning. But before I'm showing you, I'm presented you about the hardware accelerator. It's important we talking a little bit about reconfigurable computer. Okay. Because when I say about hardware accelerators, it's important to understand about reconfigurable computing, yeah, and specialized hardware, yeah. It's what is a reconfigurable computing and which are the advantages, yeah. The idea is very simple, okay. When we have the computer, yeah, the GPU, the high performance computer, yeah, the conventional computing, okay. It's you always create your algorithm and you transform your algorithm to a processor, yeah, a fixed hardware, okay? For example, CPU or GPU, okay? You have constant structure, a specific structure, okay? And you transform your algorithm to a specific hardware, yeah? Of course, you transform your algorithm in a machine language to execute in a specific hardware, okay? A CPU, GPU, and the other one, yeah? The reconfigurable computing has another idea. The idea of the reconfigurable computing is you get the other way. You in reconfigurable computing, you create a specific hardware to the specific algorithm. Okay, you don't need to transform your algorithm to a hardware. You model your hardware to the algorithm. This is a main idea of the reconfigurable computing. Okay, you don't use this way. Yeah, you will use this way. Okay, but of course you don't need more this guy because you will create your hardware. Yeah, this is idea. Yeah, it's it's these structures like high performance computer or GPU, yeah, are conventional computing, okay? Because normally you have many processors and you need to use these processors, yeah. For example, in the CPU, okay, or GPU, yeah. But when you use reconfigurable computing, you don't need this guy because you will create your hardware and you will create a specialized hardware, a specific hardware to your algorithm. Okay, this is idea. Yeah, can I show you here? Yeah, this is a conventional idea. Yeah, you have some algorithm and you need transform your algorithm in another language because your processor it's a serial processor. Yeah, it's a sequential processor. Yeah, but if you use reconfigurable computing, you can create your hardware, a specific hardware. Yeah, more specialized hardware to perform your algorithm. Okay, this is the idea of reconfigurable computing. Yeah, and of course, if you use reconfigurable computing, you have you can create a accelerator, a hardware accelerator. Yeah, because you can create a specific deep learning algorithm in hardware. Yeah? Okay, about FPGA. Yeah, today FPGA it's a it's a technology that you can make a reconfigurable computer. Okay, it's important you understand that FPGA is just a technology that you can make a reconfigurable computer. Yeah. Now I'm going to show you several works that I have been making, yeah, using specialized hardware, okay, dedicated hardware using machine learning, deep learning, and other one, okay, and I'm gonna show you some videos too with you can accelerate your deep learning algorithm, okay. In this case, for example, we implemented, yeah, cancer detection, okay, in hardware, yeah, using a fully connected neural network, yeah, in FPGA, yeah. The advantage here, because we can perform the cancer information more fast than if you use some app in the mobile phone, for example. Yeah, it's this work is published, and you guys can see. Okay. In the another case here, we implemented in FPGA. Okay. Key-learn algorithm, yeah, reinforced learn, yeah, reinforced learn with key-learn in hardware, okay, in FPGA. Here is the FPGA, yeah. In our work has a very speed up when we compare it with other works in the literature, okay, using reinforced learning with the learning. In this case, I'm gonna show you. Sorry, I'm gonna show you a demonstration. Yeah, using a stack spatial encoder. Yeah, in hardware. Okay, we are using. I don't remember the number of the layers. This is, yeah, this is the neural network that we use it. Okay, the number of neurons. Okay, we use it a systolic array strategy. Yeah, and in this demonstration, you can see the MNIST data set. Okay, in the right side, it's a hardware accelerator. Okay, and in the left side, it's a conventional computer. Okay, so you can see in hardware accelerator, yeah, you have a high speed up that we compared with the conventional structure. Okay, yeah, this is a case. This is another case that we have k-means on specific hardware. Okay, of course it's not a deep learning, but it's a machine learning. Yeah, and here you can see the comparison. Yeah, the comparison with conventional computer. Yeah, and specialized hardware. Yeah, in the hardware accelerator. Yeah, okay. Here in the left side, it's inside in the hardware accelerator. Okay, there are four k-means instances in parallel. Okay, yeah, and this one is in hardware, and another one in the right side in the conventional computer. Okay, and in this demonstration, we repeated several times the algorithm in the conventional computer and the hardware. Okay, and you can see that in the hardware, the hardware performs 40 times, and conventional computer just 8 times. Okay, you can see here the difference of the performance. Okay, in the hardware accelerator and the conventional scheme. Okay. And the other implementations, it's here it's SMO algorithm. Yeah, SMO algorithm that you can use in SVM neural network. Okay, here it's other strategy that we have been working that we transform Python implementation in FPGA implementation. Yeah. So it's because in the all last case we create a specific hardware. Okay. Now we have been working in a platform that transform Python language to FPGA implementation. Yeah. To make a high performance FPGA implementation from Python implementation. Okay, this is a very interesting application that we have been working with hardware accelerator. Yeah, in this case we are accelerating several kinds of the algorithms like machine learning and the other algorithms. Okay. But in this case, it's an interesting case because in several applications, you need to execute in local, okay? Because some people said that you don't need to create a local solution because you can use the cloud. But in some cases, you can use the cloud. You need make a local acceleration. Okay. In this project that we help other biology guys. Okay, they need get information about these worms. This is a real worms, okay? And the biological people need to analyze the movements of the worms, yeah. But they have several high quality cameras, yeah, that get the worms moving, yeah. And we created several hardware accelerators to make this process, yeah, to make this processing in real time, yeah. They use several algorithms, okay, machine learning algorithms and deep learning algorithms and digital image processing algorithms too, okay. It's an interesting application that you can see now the worms moving, yeah, here. It's an interesting application that you can use the hardware accelerator in FPGA, for example, yeah. And this is another case that we have published two other neural networks in the self-organizing maps in the hardware too, okay. And this one, it's another very interesting application that we are using deep learning now, yeah. But in this demonstration, we didn't have deep learning yet, okay. This is a tactile internet demonstration, yeah. Tactile internet application, yeah. I don't know if you know, but tactile internet, it's a next generation of the internet that we will be able to sensing things on internet, okay? In this demonstration, we have two guys. These guys are in Brazil, in my university here in Brazil, and I'm in London, in UK, okay? And these guys move this globe. And when these guys move this globe, this robot in London, UK move again. And when this robot touch my finger, these guys in Brazil sense the touch, okay? They close the tactile internet loop, yeah? Okay, but the problem about tactile internet, it's about the lattice, okay? Because you cannot have a big lattice. And in this case, we are using hardware accelerators to reduce the latency in the device, okay? Of course, we have latency in the network, but in this case, we use a hardware accelerator in the master device, in the slave device. Master device, it's in Brazil, and the slave device in UK, yeah? And you can make this one works because we are using hardware accelerator. Now we are using machine learning too, yeah, inside the loop. So if you see that this moving, the globe, the robot in the right side is moving again. And when the robot touch my hand or my finger, I don't remember. That guys in Brazil sense, yeah, has this sensation, okay, yeah, this, yeah. Of course, you guys have to believe me because we cannot show the sensation, yeah. But it's other kind of application that you can use a hardware accelerator. It's not deep learning, but you can use another application. Okay. So we have been using hardware accelerator in other algorithms, yeah, in other algorithms, and finally I'm gonna talk about the distributed computing. Okay. Again, the picture, okay, that we can see all the unit processors, okay, inside of the convolutional neural network, yeah, and now the idea is you change the structure, but you will use the distributed computing to accelerate, yeah, that I said before, yeah, that I said before. So we can use in distributed training, for example, where each layer or each part stay in the several nodes, okay, on the edge, yeah, on the cloud, and you can distribute it all information, yeah, or you can use the federated learning and you can share the deep learning model, yeah, the consensus model. It's sharing to all the nodes, yeah. The federated learning, it's a distributing a strategy to accelerate training, yeah. You change the architecture, yeah, that I said before, or you optimize your algorithm, or you optimize your structure, yeah. These are two ways that you guys can accelerate deep learning, yeah. I think it's the message of the tutorial, yeah. Or you optimize your algorithm, yeah. Sorry, or no, and yeah, because you can make both, yeah. So you can optimize your algorithm and you can optimize your structure, yeah, using hardware accelerator, distributed computing, and other kind of processors, and pruning, quantization, yeah. And you why? Because we need high throughput with low power, yeah. You remember that I said when I started this tutorial. That's it, yeah. Thank you so much for staying here for watching my presentation. I'm available to question, or if you have make more some specific question, this is my my email. I can share information and other material. Yeah, I'm really open. Yeah, I don't know if someone has some question about. Okay, if anyone has some question, so I'm saying thank you again for watching my tutorial, and I think that I can I can I can leave. Yeah. Sorry. There is a question in the chat here. For big neural network like AlphaZero, can the FPGA use or will it not be powerful enough? Very, very good question. Yeah. Today, because when you talking about FPGA, we need to talking about the logical cells. Yeah, the logical cells is the minimal, yeah, the minimal processors inside the FPGA. So when you have many logical cells, you can make a big circuit, yeah, because the size of the circuit it's proportional to the number of the logical cells inside the FPGA. Now at the moment, the big FPGA that we have, the commercial big FPGA, I think it's a ultra scale from Xilinx, okay? I don't know, maybe we have about 1 million, more I think, 2 million logical cells, okay? Logical cells, yeah. But 2 million logical cells is not enough to AlphaZero. It's not enough. One FPGA ultra scale you can implement. Sorry, if you implemented all parallel, okay? You imagine you create a specific circuit, a specific unity processor inside in FPGA. So one FPGA is not enough, but you can use several. You can use several. You can distribute it. You can make a distributed processing in several FPGAs. Yeah, and it will be possible. Yeah, for example, you can use the Amazon Amazon Cloud. You can use cards, okay, with 8 FPGAs inside in the same card, and you can use a distributed process using this one. Yeah. But I think that AlphaGo is a very, very big one, and you need use more FPGA that you want to make all parallelization, okay? But of course, there are other strategies that you make some parallelization, but not fully parallelization, and you can use FPGA. Yeah. Yes, another question, can we combine FPGA and GPUs together to make, yes, GPU, FPGA, and CPUs, yes. We have been that, yeah. We have been that using GPU together, FPGA, yeah. There is a name for this. I forgot. Sorry, I forgot now. But there is a name specific for this, yeah, but it's possible, yeah. Welcome. Another question, guys? Okay. So many thanks. Okay. I'm gonna leave. Okay.